All right, so we've got some convection, conduction, and advection. And that would be a nice, simple, easy way that things move through the atmosphere to get solar energy from one place to another, mainly from the equator to the polar regions, and then infusing the equatorial regions with cooler energy, or the lack of energy, cooler temperatures, back to the equator. But it doesn't work that well because there's stuff in the atmosphere. We've got clouds and we've got dust from volcanoes and from industrial activities, and such as harvesting of fields or manufacturing. And then we've got lots of different gases in the atmosphere that change because of the respiration of plants, or the release of methane out of oceans. All of those play into effect. They have regional conditions. So, dust from a volcano might be going off in Italy, so it's going to have a very localized or regional effect that's going to interrupt that rotation and distribution of solar energy. Harvesting of plants in Iowa in the winter or in the fall is going to then disrupt that solar energy rotation on the sides of Iowa. But we know Iowa is not the only state that's undergoing harvesting. Pretty much the whole Midwest and large swaths of Canada and Europe as well. So the regional effects are multitude. In terms of the dust generated by agriculture, we know because of cloud forcing and greenhouse forcing that solar energy is deflected by where clouds are. And we know that at the equatorial region, we've got a nice big band of clouds that are generated. So all of these things influence at different times because of the incident rates of all of these different variables, the nature of how energy is transferred at a particular location at a particular time. And some of it is seasonal and some of it's incidental, based on other driving forces such as the rock cycle and plate tectonics, or industrial activity, and when manufacturing is ramping up or slowing down. So solar energy is not as easy to track because of those conditional conditions right now. I am thinking primarily right now of the forest fires in California. Lots and lots of ash in the skies right now that are disrupting the volume of solar energy that over those areas, and then to the east of those areas into Nevada and points further east. With air and air mobility and generally circulation, it's important to understand something called adiabatic warming and cooling. And I have what I think are some really nice demonstrative videos for you to watch to help appreciate how adiabatic warming and cooling happens. But the adiabatic process is warming and cooling based on expansion and compression. So it's we're not adding any more energy or more heat to something to cause it to expand or to contract. It's the intrinsic amount that's already in that atmosphere. And I generally use the example of standing at a bus stop when you are a kid at K to 12, for those of us that rode the bus. In the winter time, when everybody was cold, even if you didn't like the person, you kind of came in close together because of your conserving heat energy. So when things are cold, you have compression or contraction. And as you're next to each other, there's a heat energy exchange and you start to get warm, right? Um, as you start to warm up and the other people start to warm up, you might spread out a little bit. You're definitely going to see this in the summertime. No, people at bus stops do not stand close to each other in the summertime. They give each other lots and lots of room. In the wintertime, strangers will stand closer together for the most part, because you're conserving heat energy and you're generating heat so that it's being exchanged and not lost to the atmosphere. So this basic principle then happens in the atmosphere, and it happens at what we gave you the other day at the average lifting rate is we're going to lose 3.5 degrees Fahrenheit for every 1,000 feet of elevation gained. All right, for every 1,000 feet of elevation drop, you're going down, we're going to gain 3.5 degrees Fahrenheit. And that's because as you go up, the atmosphere is expanding, the molecules are further apart. When they're further apart, the energy that they're giving off is being given off into the atmosphere. There's more space between the molecule and everything else around it, right? So you don't have as much heat generated, and you're losing heat as you go up. As you're coming down, you've lost some volume of energy. The molecules aren't moving as fast, they're moving slowly, so they're going to dense, they're going to come in closer together, so they're going to fall through the atmosphere, and as they get close together, they're going to start to heat up. And as they heat up, then they expand again. And as they expand, they're going to start to lift. They get up to a place where the lift is no longer possible. Then they contract and they fall again. So the expansion and lift go together. Then the contraction and fall go together. So we're generating heat on the contraction. When we're close together, we're expelling heat on the expansion. So lifting, when we lift, the air is cooling by expansion. And when we are falling, the air is falling, it's compressing. And as it compresses, there's a greater exchange of energy, so we've got some heat. So if you like a diagram, that's what I've got next for you. So out of your textbook, what we see is the air is nice and warm down here, and it's expanding. The particles are increasingly getting farther apart. As there's farther apart, we're getting heat energy lost. We lose enough energy, this starts to compress and then fall back down. So you can kind of see in this diagram, we've got lift, and then just like convective rotation, falling, and then we get lifting again. So we can start to see how there could be a rotational effect that is self-generating occurring. All right, guys, next set of slides.